Analysis of the fire effectiveness of naval weapon systems against surface targets. Aim of every firing mission is to directly hit the target or to fall the rounds within a specified area that it can kill or incapacitate the target. Even though first round hitting the target is the most desired condition, it is highly unlikely in actual firing missions, even with sophisticated systems and controlled conditions. Several rounds fired from a single gun within a short time under same conditions would follow different trajectories, forming a conical beam. The impacts found to be dispersed on the ground or sea around a central point called the mean point of impact. Projectile leaving from the gun barrel follows a curved path or trajectory due to Earth's gravitational pull. Trajectories in the vacuum and air differs due to presence of air resistance, as you can see on the screen. There are many factors and error sources affecting the accuracy of rounds fired from a naval gun weapon system. Some factors or the errors can be determined and eliminated, or else compensated. Some are random in nature and cannot be eliminated. Due to variability and complexity of these parameters, it is not practically feasible to measure the fall of shots. Hence, we have to consider error probabilities caused by these random variables by estimation. Statistics is the branch of mathematics that deals with such cases to determine firing accuracy and ultimately the effectiveness. A problem. Kothalawala 76x62mm compact gun weapon system was the highest caliber and one and only fire control radar coupled weapon system Sri Lanka Navy had by 2019. This weapon couldn't use effectively during the war due to some defects, and its effectiveness was never calculated, and we don't have such method also. Objectives. There are three. My first objective is to introduce a calculation model for analyzing fire effectiveness of an indirect fire naval weapon system against surface targets. Second, to calculate the single shot hit probability and analyze fire effectiveness of Kothalawala 76x62mm compact gun weapon system against various surface target settings. Third, to influence the future researchers in Sri Lanka to conduct projects for weapon system optimization. Naval weapon system firing process. Initially, the detection is done using the ship's search and surveillance radars. After detecting a target, then the target identification is done with the available records and maybe using EW. Then the target acquisition is done by using the fire control radars and maybe the electronic devices. Then the target tracking to obtain the bearing range and speed of the target. Then predicting the target's future position. Afterwards, entering the ballistic corrections would be done for the changes from the standard conditions. Then continuing providing of the lead by the fire control system whilst giving the stability corrections. That means the corrections for the pitching and rolling movements of the ship. Then providing of gun laying orders will be done through the servo system. These orders are given to the gun as training and elevation angles. Finally, the firing commences when the target reaches the maximum effective range of the particular weapon system. Afterwards, you can do corrections as splash corrections observing the fall of shots. So for every gun weapon system, there are standard shooting conditions given by the manufacturer when the gun is proved, maybe in a proving ground. So the weather, location and material standards are given for each and every weapon system, as you can see on the screen. The standard shooting conditions given for particular gun weapon system are never met in actual firing environments. These varying conditions pave the way for firing errors, ultimately affecting the desired accuracy. So when classifying firing errors, the systematic errors, fixed bias errors means the constant errors because the value is not changed with the time. Variable bias errors means the value changes occasion to occasion but follows a certain rule. We call it accumulation errors. MPI error is an example. The random errors mean the worst case because the value and the sign of the error changes randomly. So round error is the example. Methodology. Whilst various factors affecting the firing accuracy, the observable outcome is the deviation of shot from the target, or we call it desired point of impact, in range and deflection. Therefore, we should find or predict the amount of deviation from the DPI to determine the accuracy and subsequently the fire effectiveness of the weapon system. There are various methods, but what I choose as user-friendly method is the analysis method using the formula calculation. Fall-off shots around the MPI are recorded as missed distances in range and deflection. So these X and Z are independent variables, as you can see on the screen. Then the fall-off rounds fired from a naval weapon system considered to follow the bivariate normal distribution as shown in the figure with an elliptical base representing the area of dispersal. The probability density function of that pattern of distribution of shots on the coordinate X and Z as used in most weaponizing tools can be expressed as of formula 1. Here the mu x and mu y are means and the sigma are standard deviations. According to our problem, the single shot hit probability against a rectangular target is obtained by the formula 2 and formula 3. Expansion is in the formula 3. Here the Lx and Lz denote the target size. So the coordinate system which I use for this study is very important. The elliptical shape denotes the distribution area and the rectangle is the target. So our ultimate aim should be to place the ellipse on the rectangle. Once the ellipse touches the rectangle, that means a hit. Calculation model for obtaining the probability is designed considering the dispersion error, that means round error, and the aiming errors. Aiming errors is considered under servo system, fire control and observation equipment errors, and the ballistic metrological error. So the first model is for the calculation of probable dispersion error, as you can see on the screen, in range and deflection. Then the model for the servo system error, it is also in the tracking and error in the direction and range. Calculation of observation equipment error. Here observation equipment in the sense we have radar and EOD means electro-optic devices, that means for the photoelectric tracker. Here the both system and random errors are available. Again, the calculation model for the fire control system, as you can see on the screen from formula 11 to 14. Then calculation model for the ballistic metrological error, very important. First is error caused by the muzzle velocity deviation. That is because each and every ammunition of the projectiles are not similar. There are a lot of variations. So that causes or induces error. Then model for air density deviation. Then the ballistic wind deviation. There are two vertical and horizontal ballistic winds. So vertical wind error is responsible for the range error and the other one is for the deflection error. So finally, the combination is done through using the root sum square method, and this model is run in the MATLAB program for varying target conditions to obtain the hit probability. My typical target setting would be the attack draft of the LTT and the suicide draft, and as the largest target, I use offshore patrol vessel. Then the results, first, the probability against the attack craft when the range changes from 500 meters to 5,000. So there's a significant reduction of the probability with the range, and after 2,000 meters, it is going to normalize. Then with the change of the relative bearing, what I observe is when the relative bearing is 60 degrees, I have the maximum hit probability. For the change of falling angle, 15 degrees of the falling angle provides the maximum hit probability. Then for the suicide draft, range change is also same, and for the relative bearing, when the angle of attack for the target is 75 degrees, I have the maximum probability. For the largest target, the OPV, when the range changes, you can see how the results came for the probability, but the significance is up to 2,000 meters, there's a very good probability, but after there's a rapid drop of hit probability, and it is again normalized after 3,000 meters. So unless from the effectiveness calculations, hit probability is largely dependent upon the target range. Hit area of the target is crucial factor, and that is decided by the angle of attack and the angle of fall. There's a pattern of single shot hit probability change related to target range, relative bearing, and the falling angle of the projectile. Knowing that is beneficial for before planning any firing mission. It is important to know the inherent errors of the associated systems, and due consideration should be given for the mechanical errors and the equipment alignment. Accuracy of met message is very important factor, especially in long range firing. So it is better to have systems on board to obtain weather parameters in situ. And I found following issues with this study. Firing table data, probable equipment errors are taken from the Chinese sources, so there may be some sort of compatibility issues because I couldn't find those data from our weapon systems. Then the status of both firing platform and target moving was not considered for this study, and there was no impact records or proving ground test records available for comparison purpose. I have future plans. First, to design a computer-based program for simulating the gun projectile trajectory. Then, to design a fire effectiveness calculation model against fast-moving targets and air targets, because that may induce some additional errors. Introducing all of the above to SLN, or Sri Lanka Navy, in view of conducting prior studies on a particular weapon system before acquiring them into the Navy. So these are my references, and thank you very much.